The next few examples include non-integer denominators. This example specifically has a denominator of 5.5. Well, what is 5.5? Well, 5.5 or 5 5/10 is a decimal. Its value is equal to 5 1/2, which is a mixed fraction. How do I know that 5.5 is equal to 5 1/2? Well, if you solve 1 divided by 2, that is 1/2. But anyway, if you solve 1 divided by 2 by using long division, you will get 0.5. The next question I would like to answer is, how do I get a denominator of 5.5, of 5 1/2? How can I visualize that? Well, one common way of visualizing fractions is parts of a circle. So to visualize a denominator of 5.5 of 5 1/2, I would need 5 1/2 pieces to make up the circle. And I have 1 piece, 2 pieces, 3 pieces, 4 pieces, 5 pieces, 5 1/2 pieces. I would like to note that this smaller piece is not 1 over 5.5. It's not 1 over 5 1/2. It is only a half of a piece anyway. It will be a half over 5.5, a half over 5 1/2, or 1/11. The next point I would like to make is that 5 1/2, which is a mixed fraction, is equal to 11 halves. How can I know this? Well, let me quickly use toothpicks to explain why. I split up each part that is bigger than the leftover part into 2 parts, thus creating all halves. And how many halves do we have? 1 half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves, 8 halves, 9 halves, 10 halves, 11 halves. And all I did was simply add toothpicks. So therefore, 5 1/2 is equal to 11 halves. So why would this matter? It means that we're not only solving 3 over 5.5 plus 7 over 5.5. We're also solving 3 over 5 1/2 plus 7 over 5 1/2. We are also solving 3 over 11 halves plus 7 over 11 halves. Why is this? 5.5 is equal to 5 1/2, which is equal to 11 halves. We can simply substitute into the equation. For example, if I have a 5.5, I can substitute a 5 1/2 for it. Therefore, we can know that 3 over 5.5 is equal to 3 over 5 1/2, which is equal to 3 over 11 halves. Likewise, 7 over 5.5 is equal to 7 over 5 1/2, which is equal to 7 over 11 halves. It does not matter if the denominator is a decimal, a mixed fraction, or an improper fraction. As long as it has the same value, it is the same example. Now let's solve 3 over 5.5 plus 7 over 5.5. First of all, we're going to need 3 over 5.5. Well, here I have 1 over 5.5. Here I have 2 over 5.5. And here I have 3 over 5.5. Now, let's get 7 over 5.5 more. So here I have 1 over 5.5, 2 over 5.5, 3 over 5.5, 4 over 5.5, 5 over 5.5, 6 over 5.5, and 7 over 5.5. Now let's figure out what the total is. We have 1 over 5.5, 2 over 5.5, 3 over 5.5, 4 over 5.5, 5 over 5.5, 6 over 5.5, 7 over 5.5, 8 over 5.5, 9 over 5.5, and 10 over 5.5. Therefore, 3 over 5.5 plus 7 over 5.5 is equal to 10 over 5.5. Third thing to notice is that if we had solved 3 plus 7, the way of solving it would be a whole lot similar to solving this problem of everything being in 5.5. The only difference between solving 3 plus 7, the difference between solving that and solving 3 over 5.5 plus 7 over 5.5 was that everything was over 5.5. So this means that you add the numerators but keep the denominators the same. I would like to show that we can know that 3 over 5.5 plus 7 over 5.5 is equal to 10 over 5.5, but without using a model. We do not know that this is true yet. First of all, let's substitute the 5.5 for 5 1/2. Exchange the decimal for the mixed fraction. Why can I do this? Why do I know that 5.5 is equal to 5 1/2? Well, if you were to solve 1 divided by 2 using long division, which by the way would be 1/2, you would get 0.5. Now we still do not know that the second line is true. Now let's exchange the mixed fraction for the improper fraction. 5 1/2 is equal to 5 plus 1/2. That would be equal to 10 halves plus 1/2. 10 divided by 2 is equal to 5, so I can change the 5 to 10 halves. Now I do know how to add these two fractions because the numerators and denominators are positive integers, and I already know how to add such fractions. You add the numerators but keep the denominators the same, and I get 11 halves. So I go ahead and exchange the 5 1/2 for 11 halves. We still do not know that this is true yet. We still have a non-integer in the denominator. Well, let's change the 3 over 11 halves like so. Well, I know it is equal to 3 over 1 over 11 halves because 3 divided by 1 is equal to 3. Anything divided by 1 is equal to that anything. The line you see in fractions is another way of writing divide, so we can exchange the middle line for the divide side like so. We can rewrite it as 3 over 1 divided by 11 halves. When you divide two fractions together, you keep the first fraction as so, change the divide sign to a times sign, and then flip the second fraction. And that would be 3 over 1 times 2 over 11. I plan to explain why you can do this in a future set of videos, and when I create that future set of videos and publish it, I plan to link it in the description of this video. Anyway, when you multiply two fractions together, you multiply the numerators and multiply the denominators. Again, I plan to talk about this in a different future set of videos, and again, when I create that, I do plan to have that linked in the description of this video. And that would be 6 over 11. Another way to think about this is how I like to think about it, is you can bring the 2 to the numerators. The reason for why you can do that was explained in the previous yellow box, and that would be 6/11. And so, for similarly reasoning, you can do the same thing, same idea for 7 over 11 halves and for 10 over 11 halves. And we end up with 6/11 plus 14/11 is equal to 20/11. Now we actually do know this is true. Why is that? Because the numerators and denominators have positive integers. we do know how to add fractions like so. You add the numerators but keep the denominators the same. And because we know the last line is true, we know the third line is true, that the second line would be true, and that the first line would be true. Now we do know for 3 over 5.5 plus 7 over 5.5 that it is equal to 10 over 5.5. And for this case, you do add the numerators and keep the denominators the same. The next video for this set of videos is part 7b, which is the second example when you include non-integer denominators. If you would not like to watch any more examples for this case, feel free to click on the second link, which includes part 8, which is when you include a numerator of 0, and it also includes part 9, when you include a denominator of 0.